Assalamualaikum and hi. Today we are going to present a presentation of journal paper review of potassium oxalato ferrate trihydrate. Okay, so we are from Group H8. So our members are Amir Rahimi, Sharifah Hazita, which is me, Jasbinder, Adwa Afrinan, and Nurul Suhada. Okay, first we will present about method of synthesis. So for method of synthesis, okay, for the first one, we will add 5.5 gram of potassium oxalate monohydrate in 100 ml of water in 100 centimeter cube of volumetric glass, and we will heat it in a steam bath. After that, we will continue stirring it while adding 2.7 gram of iron-free chloride and hexahydrate, and it will slowly form a green crystal, and we will turn off the steam bath, and we will add the mixture into the ice bath to make it a further crystallization of green crystal. After that, we will filter it using Bushnell funnel to get pure crystalline solid of our product. But our product is not impure, it's not pure because it contains a lot of impurities, so we need to dissolve it in hot water, and then we will only get the pure product, which is we filter it back again by using 10 of propanol, and we will let it cool in dark cupboard before we weigh it. Okay, next I will pass it to Amir for point group of determination.
All right, hello everyone. For my part, I will be representing about the point group determination. All right, what is a point group? Point group describes all symmetry operations that can be performed on a molecule that results in a conformation indistinguishable from the original. All right, there are 5 symmetry operations, which is E, identity, C, an axis of rotation, where at a point we can rotate our molecule, and sigma, a plane of symmetry, which is the molecule can be reflected and still look the same. I, which is an inversion center or a center of symmetry, which is the molecule can be inverted and still look the same. And S, which is improper rotation axis, where the molecule can be rotated and can be reflected and still look the same as the original. All right, for our compound, which is potassium trisoxalato ferrate 3 trihydrate, the coordinate compound which is trisoxalato ferrate 3 ion has 3 symmetry operation, which is E, identity, and C3, we can look at 3 oxygen atom at the top and at the bottom, which we can rotate it 120 degree. And also C2, which is the line is through the center atom and passing the oxalate ion, which we can rotate it 180 degree. So for this compound, it has no symmetry plane, no inversion center, and improper rotation. So the point group for this compound is D3. All right, that's all from me. I will pass my presentation to Jasmine.
Okay, now I will be presenting about type of ligand bonded. So type of ligand. So for the ligand for the potassium trisoxalato ferrate 3 trihydrate is oxalate group, which is also known as the bidentate ligand. So oxalate group is the bidentate ligand. What is bidentate ligand? Bidentate ligand is the Lewis base which will donate 2 pairs of electron to the metal atom, which is the oxalate will donate 2 pair of electron to the ferrate. So now the ferrate central atom will have a coordination number of 6. That means the ferrate central atom will form a geometry of octahedral. So the oxalate group is actually known as a weak field ligand. Why it is a weak field ligand? Because the ligands are having a low splitting of d orbital. So when it has a low splitting of d orbital, it will have a delta O parameter smaller compared to the energy of a pairing of electron. So therefore, the electronic configuration of the d orbital of the Fe3 plus is d5. Next. So now I'll be explaining about the valence bond theory, in where formula for potassium oxalato trihydrate is K3FeCQ043.3H2O. And now I will explain you about the oxalato ferrate 3 ion, in where its oxidation state is 3 plus, and the electronic configuration of Fe3 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, since it has the D5 configuration. So now I'll show you the hybridization diagram, in where at ground state the Fe3 plus will have 5 electron which will partially fill the 3d orbital. So when the 5 electron from the 3d orbital partially fill 3d orbital hybridize, it will form a 3d orbital with hybridized sp3 d2 orbital and also unhybridized 4d orbital. Next. So the conclusion for the valence bond theory is it becomes an outer orbital complex of hybridization because of the effect of weak field ligand, which is due to the lower splitting d orbital, and it is an high spin complex which adapts the crystal structure of octahedral, since the metal atom will have the coordination number of 6. That's all from me. I'll pass to my another friend.
Okay, thank you, Jasmina, for explaining about VDT just now. So I will continue about crystal field theory. Okay, so as Jasmina said just now, oxalic ion is a weak field ligand. So it has a high spin and low splitting and low delta O. Okay, why oxalic ion is a weak field ligand? Because it causes only a small splitting of energy levels, due to which it is energetically more favorable for the electron to occupy the upper EG level rather than pairing up in the T level. Okay, so for the Dn configuration for Fe3 plus is D5, because it is a half-filled D structure and is particularly more stable. Okay, so for the splitting octahedral energy is lesser than the pairing energy, because as we know, splitting octahedral energy for this complex is paramagnetic, in a paramagnetic state, because all electrons are unpaired. So that is why it has a lesser energy than the pairing energy. Okay, so for the configuration of the system is P2G 3EG2, and for the CFSE, okay, for the CFSE, for an octahedral complex, an electron in the most stable T2G subset is treated as contributing negative 2.5 here, whereas an electron in the higher energy EG is contributing in positive 3/5. Okay, so why we have 3 and 2 here? Because at here we have 3 unpaired electrons, so 3 times with negative 2.5 plus with we have 2 unpaired electrons here times with 3/5, and we get the value of 0.0 delta O. So next I will continue about the ligand field theory. Okay, so although we all know that oxalic ion is a pi donor ligand. Okay, so pi donor ligand is a kind of ligand which is endowed with the field non-bonded orbitals that overlap with metal-based orbital. So their interaction is complementary to be behavior of pi donor ligand. Okay, so an oxalic ion can donate 2 pair of electrons either from the 2 oxygen atoms having negative formal charge, or from 1 double bonded oxygen atom and 1 negatively charged atom. Okay, so as we can see here, for the homo-LUMO separation, this is the homo-LUMO separation, nu delta O is decreases because the greater the mobility of the pi electrons in large conjugated pi orbital system, the greater the distribution of the energy throughout the molecule. So this is what it makes the molecule become stable. So hence the delta O will be decreased. So next I will pass to Adwa Afrina about spectroscopy.
Okay, thank you, Azika. Now I will explain the spectroscopy for IR and UVVs. Next. So this is the IR spectrum for potassium triisoxalato ferrate trihydrate. So first we can see there are peaks at wave number in between 3429.43 to 3587.6, which is indicates that there are OH stretching bond. And then second, we can observe peaks at wave number in between 1716 to 1643, which indicates the CO stretching bond. And then third, we can observe peaks in between 1253 to 1273, which is indicates the CC stretching bond. So OH stretching bond we can observe from the OH from the water molecules, and then CO stretching bond, and then CC stretching bond from the ligands of this complex, which is oxalate. Next. So this is the UVV spectrum. So for this complex, the lambda max is at 210 nanometer and the absorbance at 1.95 absorbance. So the lambda max is at 210 nanometer. This complex is like at ultraviolet region. Next. So this is electronic transitions. So the ion 3 plus for this complex has a high spin D5 configuration. So from the D5 Tanabe-Sugano diagram, we can see that for high spin, the ground term is sextet A1. So from the diagram, we can see that no excited state that have same spin multiplicity, there's no spin allowed transition. So as a result, the electronic transition for this complex is spin forbidden. So if we recall what we have learned, spin forbidden is allowed if spin orbit coupling is taken into account. So next. Now I will explain the magnetic properties. Next. So the coordination number for this complex is 6 and the geometry is octahedral. And then ion 3 plus is D5. The ligand in the complex is oxalate, which is a weak ligand, hence it has high spin. So based on the energy diagram above, there are unpaired electrons on T2G orbital and EG orbital. So therefore, this complex is paramagnetic. Next. Okay, now I pass to Sahada to present the model of metal complex.
Okay, now I will show the model of the metal complex. So here is the 3D model of potassium triisoxalato ferrate 3 trihydrate. Ferrum 3 plus is the central metal ion, which is surrounded by the 3 groups of oxalate ions, which is a bidentate ligand. So it has 2 points of attachment. And here are the potassium and also 3 molecules. Okay, next. Okay, now I will explain on the applications of potassium triisoxalato ferrate 3 trihydrate. Next. Okay, it is used as a sensitizer in cyanotype photography. It is a photographic printing process that produces blueprints. So it uses a mixture of ion compounds, which is ferrum 2 plus and ferrum 3 plus, which will be exposed to UV light and washed in water oxidized to create a Prussian blue image, which is the blueprints. Okay, so potassium triisoxalato ferrate 3 trihydrate is used as sensitizer because it's an extremely sensitive actinometer, which means that it can react well with light. Okay, next. The process of cyanotype photography is firstly, we have to mix the solution of potassium triisoxalato ferrate 3 trihydrate with potassium ferricyanide and coated them on a sensitized paper. Sensitized paper is paper that will produce the final blueprints image. And then we will put a negative image on top of sensitized paper. Negative image is image that we printed on a translucent paper. And as you guys can see in the picture below, they also put a glass sheet and clamp on top of it to avoid any changes in position and also to produce sharp image. And then the paper will turn to pale yellow, which means that it is ready to be washed. So we will rinse it with water to remove any excess of sensitizer, and it will then turn to blue color. So to increase the intensity of blue color, we will add hydrogen peroxide solution. Next. So the reaction that occurs throughout the process is that when ferrate oxalate complex absorb the light, it will cause electron transfer that reduce ferrum 3 plus to ferrum 2 plus. And then the newly formed ferrum 2 plus will react with ferrum 3 plus from ferrocyanide ions to form blue precipitate, which is the Prussian blue. So here are example of image that has been shown in the journal article. Okay, next. So here are next the list of references that we use for the presentation. That's all from our group. Thank you.